We've discussed black holes and their somewhat strange characteristics, or shall I say very strange characteristics. In the last part now, let's look at evidence for black holes. They don't emit light, but they modify their surroundings through their gravitational influence, and in that way can be observed. A black hole has stronger gravity than a neutron star, especially as you get close to it. So it should be surrounded by a very hot X-ray emitting accretion disk, for the same reasons that white dwarfs and neutron stars produce accretion disks, stealing gas from a binary companion, etc. The type of corpse that's in an X-ray binary is going to be determined by the mass. So we see these binary systems, evidence of binary systems emitting X-rays, and that's a key indicator that it is a very high mass stellar corpse if it's emitting X-ray radiation because of the extreme conditions for that. Here is a table of 9 black hole candidates. They're candidates because these objects that are binary systems are massive enough that they've exceeded the 3 solar mass limit of a neutron star. So when the compact object exceeds that 3 solar mass, there's really little doubt that they're anything other than a black hole. These candidates here are all falling into that category. It's a compact object greater than 3 solar masses, and therefore they must be black holes. Let's consider one of these high mass compact objects, an object known as Cygnus X1. And it's in the beautiful constellation of Cygnus the Swan, so right about here. You can, even in the Chicagoland area or light polluted areas, wherever you're looking from, you can see Cygnus. Well, this object is associated with a binary companion that's a supergiant B0 star. So it includes that supergiant blue star and the compact object. It's a very promising candidate. It's been very well studied and manifesting the characteristics that reveal that in fact it's a black hole. The blue supergiant star has about 30 solar masses. And the unseen companion, which is shown very well in this artistic rendition here, reveals the accretion disk, and it is an accretion disk around an object that's too massive to be a neutron star. So the gases accreting around the black hole are going to be superheated because of the circumstances, the processes that we've discussed already. And as you get close to the black hole, as the gases spiral in, they heat by friction, magnetic fields, so that just outside the black hole you should see emission in the X-ray, and that's in fact is what's seen. So that is all coming together to reveal that we're looking at a black hole binary system. Well, a black hole in binary with a B0 supergiant star. So how can we tell if the compact object in binary with a large stellar companion is a black hole or a neutron star? Well, by the mass, fundamentally, as we just discussed. Greater than 3 solar masses, the compact object is a black hole. In addition to that, we can gain information about the nature of the emission of X-rays from the compact object. If it's a neutron star, for instance, then the infalling matter can produce bright spots in the center. So we have these bright emission from the center region of the neutron star. A black hole, on the other hand, will not have any emission coming from anything inside the event horizon. So there's no surface for the material to fall onto, and it just disappears without a trace inside the event horizon. So looking at the characteristics of the X-ray emission coming from this compact source gives us additional information as to the nature of the compact source, whether it's a black hole or neutron star. Black holes do not come only in stellar mass sizes. There's also larger black holes that can exist. So we have supermassive black holes in the centers of galaxies. As a case in point, we have here in this galaxy NGC 7052 a 300 million solar mass black hole revealed by the accretion characteristics shown as super bright cores emitting lots of X-rays. And these galaxies, they don't need a stellar companion to feed gas to them. They're feeding on everything in the galaxy. They're controlling the galaxy. So they have lots of fuel to feed their supermassive black hole, which emits copious quantities of X-rays. So this is really actually a typical feature of galaxies. We're seeing most galaxies seem to have these supermassive black holes. Our own galaxy has a supermassive black hole at its center, revealed by careful study of orbital characteristics of nearby stars orbiting a black hole and revealing its mass to be very large. We'll investigate that in our last unit. And here is, in addition, a galaxy that has a 500 solar mass black hole, M82, and it has an X-ray source offset from its center that varies in brightness. Huge intensity variations, X-ray source. And this has been determined to be a black hole of about 500 solar masses. So the evidence is emerging for black holes in various places of high star density that range in the hundreds to thousands of solar masses. These are known as intermediate mass black holes. There's also primordial black holes that could have emerged from the Big Bang itself, but this is a little more speculative, and we don't have direct evidence for these objects. Potentially the most energetic emissions ever observed in the universe are not what you might think so far in your developing understanding of astronomy, namely you might say supernova, but they're rather gamma ray bursts. Gamma ray bursts are almost unimaginably intense emissions that have had astronomers scratching their heads for quite a few years. Lots that is not yet understood, but the story is starting to come together. Here's a gamma ray burst recorded in 1999, a day after the burst itself, and then 2 days later. Over here. Well, the general features of gamma ray bursts, they are massive bursts, incomprehensibly almost, that come from outside of the Milky Way galaxy in general, not in the plane. So here is a map of gamma ray bursts, and you can see distributed throughout the entire view of the sky in all directions, somewhat randomly dispersed, therefore not associated with the Milky Way galaxy in particular, which was a huge question that has subsequently been answered. Because they're so bright, it seems like they need to be closer, therefore in the galaxy, than what they appear to be, which is coming from outside of the galaxy. Well, they are coming from outside of the galaxy, even billions of light years away, and are so bright even at those distances that it's, once again, as many things in astronomy, seems almost impossible. They typically are categorized in the short, which are milliseconds or less than a second, and long gamma ray bursts, typically somewhere around 40 seconds, maxing out at maybe about 15 minutes or so for the duration of the burst itself. They peak and fade away quickly in general, so it's hard to study. How do you get a spacecraft or telescopes, proper technology, focus on these things to study them? That's difficult, although the afterglows may last for days. In fact, the visible light afterglow of a gamma ray burst can be as high as over 2 million times the visible luminosity of a supernova, if that helps put it into perspective. And they're likely associated with stellar phenomena, which, if you read into that little statement I just made, it's probably picking up that means we maybe just don't really know very particularly what's going on. Well, that would be true. But there is evidence that stellar processes, things associated with large stars, are associated with the gamma ray bursts as well. So what about the sources of gamma ray bursts? The biggest trouble has been their short duration and the difficulty of discovering them and basically catching them in the act. That's the problem. So there's a couple of spacecraft that have been fine-tuned to do this very well. One's a Swift Gamma Ray Burst Observatory, another one being the High Energy Transient Explorer 2. So these are very useful spacecraft that we have that are very well adapted to quickly zeroing in on the object associated with gamma ray bursts. What are some possibilities for the short duration GRBs? Well, the merger of a binary system. Okay, these are the stellar phenomena I was talking about in part. Like two neutron stars forming into a black hole in a flash of energy that would indeed exceed a supernova explosion by orders of magnitude. And so would a neutron star in a black hole, or a black hole in a black hole. These are all possibilities, each one having its own characteristic afterglow. So this is all fruitful areas of research. Here's a long duration visible light afterglow. And you see many days the gamma ray itself is associated with a host galaxy that may be very far away. So the host galaxy is pretty dim compared to the gamma ray burst itself, and in this case taken quite a long time to fade away. In fact, the long duration GRBs, they look very conspicuously similar to a supernova. The afterglow seems to match that, but just way out of kilter in terms of its intensity. But if it looks like a supernova, maybe it is a supernova. Well, a 20 plus solar mass rotating supernova event can produce a black hole, as we've discussed, especially when you get to 25 solar masses. And if it's spinning rapidly enough, the equatorial centrifugation, in other words, the tendency for it to fly apart, is battling against the collapsing forces. What you can get is the poles collapsing and the equator not. So in this way, you can get tremendous quantities of energy focused along the polar regions, so emitting onto the poles, beams of energy released along the rotation axis. So if it's pointed in the right direction, this could account for the extraordinary burst of energy revealed. The extremely energetic supernova profile also goes by the term hypernova. And so that might be what these things are, a hypernova. Looks like a supernova, but about 1 out of 100,000 or so of these supernova events, type 2 supernova, manifest this out of proportion intensity characteristic. So very likely the long duration GRBs may in part be accounted for by observing this thing called a hypernova, producing gamma rays of unprecedented proportion. And so that is our basic understanding, the state of the art of gamma ray bursts. So nothing is emitted from a black hole, right? Well, what I've been emphasizing so far is that there's no electromagnetic radiation coming from a black hole. But there is a phenomena that has been developed by the cosmologist, mathematician Stephen Hawking, where black holes actually may be able to evaporate. This is a very interesting idea, not fully accepted, but nevertheless worth considering. And it comes from the idea that particle pairs, particles and antiparticles, can emerge out of the vacuum of space spontaneously. There's laboratory evidence for this, and it's understood that this is occurring all the time at amazing rates within and outside of your body, and you have no way to detect any of it, because by definition these are called virtual particles, since they recombine and disappear before any detection is possible, something on the order of 10 to the negative 21 seconds or so. All right, sounds a little bit like science fiction, but all I can say is it's not. This is real science. If it happens to occur at the event horizon, one of these particles could get trapped while the other escapes to the outside universe. It has the potential to escape. And if that happens, the particles go from virtual to real before they can recombine. The one that is outside of the event horizon, whether it's in this case a positron, here a gamma ray photon, they can actually escape. They may or may not, but statistically some may. If they do, they will obey the E is equal to mc squared Einsteinian relation. So the mass that's lost has to obey the energy associated with that particle. So the escaping particles produce what's called Hawking radiation. Whether it's radiation or not, it may be actual particles. In this way, the black hole can eventually lose mass and evaporate. Now, for a 30 solar mass black hole, calculations reveal that it would take 10 to the 61 times the lifetime of the universe to evaporate. It turns out that the tidal forces that separate these particles is significantly less for very large black holes, so the chance of this happening diminishes greatly at the event horizon of a large black hole. So the evaporation lifetime is going to rapidly increase as well. So this is an incomprehensible time, to say the least. But just to make a comparison, if the black hole is, say, 10 billion kilograms, about the size of Mount Everest, a black hole of that size should evaporate within the lifetime of the universe. So as the black hole becomes very small, it evaporates increasingly rapidly. And when it gets to micro-sized, it can literally explode with energy as this process continues to take place. And the black hole puffs itself out of existence. Again, this is debatable. It's somewhat speculative, although substantiated theoretically. Not everybody embraces this, but gives you an idea of the possibilities for what could happen to the black hole. So now you know that it's not sufficient just to say nothing is emitted from a black hole. Although that may be true, we have this possibility of Hawking radiation being a reality. This will conclude our introduction to black holes and finishes our unit on the death of stars.